I mean, the next thing I will do is, well, how do we express these derivatives in terms of some more familiar quantities? I need to find the differential of the chemical potential, basically.
John, the other ends are also critical points, right?
Sorry?
There's three critical points and three critical. Yeah, for the other ends are also critical points, right?
Which ends?
So if we could.
You see, this line and this line, they shouldn't have any endings because what we call solids are usually crystalline solids. There's definitely a boundary between those phases. It extends to infinity. In this diagram, at least, there is one critical point where the phase coexistence line between a liquid and the gas terminates. You see, as long as you are on this line, that is the liquid-gas coexistence line, you have in the same system two phases that you can actually see the difference. But if you don't have coexisting systems, you have one system which you claim to be a liquid, another system which you claim to be a gas, well, those claims are not so well founded. That's the basic idea. As long as they coexist, you can differentiate them. There is a phase transition. But if they don't, well, let's see. I need to find the differential of the chemical potential. Let me go to my first law of thermodynamics. Let me do a trick. Well, this is basically a Legendre transform, by the way, that you also use in classical mechanics. When you go from Lagrangian to the Hamiltonian, you just take one derivative, multiply with that quantity, and subtract it from whatever you have. If you look at, let's say, this one, t is the derivative of u with respect to s. So you are basically doing the same thing. Now, that function, this one over here, is called g, the Gibbs free energy. But you see, if you look at the differential of g, g is an extensive quantity. It depends on t, p, and n. The only argument it depends on which is extensive is n. So since g is extensive, it has to be proportional to the number of particles with a function multiplied by a function that depends only on t and p. And in fact, that function is nothing but mu. Because if you take the derivative of g with respect to n, keeping t and p constant, you get mu. This is the trick that we used a couple of times before, so I'm not going into the details. So g is just n times mu. So differential of g is n d mu plus mu dn. This is minus s dt plus v dp plus mu dn. Mu dn's cancel, and now I know what the differential of mu is in terms of my other parameters. Minus s over n dt plus v over n dp. Now s over n is the entropy per particle, v over n is the volume per particle. They are usually denoted by small s and small v. But d mu, then if this is the differential of mu, derivative of mu with respect to temperature at constant pressure is nothing but the entropy per particle, and derivative of mu with respect to pressure at constant temperature is nothing but the volume per particle. So now I can simplify this derivative. This is equal to minus derivative of the chemical potential with respect to temperature is minus the entropy. So this is the entropy per particle for the B type of particle minus the entropy per particle of the A type of particle divided by derivative with respect to pressure is the volume per particle VB minus VA. Or along the coexistence line, the slope of the pressure is given by, no, sorry, there's no minus sign over here. Change in the entropy per particle divided by the change in the volume per particle. Well, during phase transitions, okay, the pressure doesn't change. During phase transitions, you have to give some heat to the system to go from one phase to the other phase. If you, I don't know, if you consider, for example, liquid-gas phase transition, you have to break the bonds between the molecules in the liquid so that the liquid becomes a gas. That heat given is called the latent heat of fusion, the latent heat. Well, per particle, the change in the entropy is the heat given to the system divided by the temperature. Well, the heat given is what we call the latent heat of fusion. So this is nothing but L over T times delta V. L, heat given to the system as one particle goes from, let's say, liquid to gas. I'm expressing it in quotes because it can be any transition between any phase to any other phase. It can be also gas to liquid. And delta V is the change in the volume per particle. As the system goes from liquid to gas. Now let's look at, now in general, if you have a gas phase, if you have liquid which is going into the gas phase, the volume will expand significantly. So in general, delta V would be positive. L will be positive. As you go from liquid to gas, delta V will be positive. L will be positive. You have to give heat during this phase change. But that means the slope is positive. So you have this slope. Now, as you go from, let's say, solid to liquid, L will be positive. You have to give heat to make your system melt. Delta V, the volume will increase in general. But it decreases for water. Ice has a larger volume than liquid water. In fact, that is why ice floats. If you consider other liquids, when they freeze, they shrink, they have a larger density, and hence, if you put the frozen object inside the liquid object, inside its liquid, the frozen form will just sink, not for water. In fact, this is one of the crucial things about water which makes life as we know it possible. Because what happens if you have some liquid ponds, as the temperature drops, the top freezes, the ice doesn't sink, it just raises, it covers the surface. Ice is a good insulator. So you can have liquid lakes even if the external temperature is much lower than 0. Well, what this tells us over here is, for example, this phase diagram cannot be for water. For water, the diagram I should have had should be something like this. The slope had to be positive for water. Any questions? Okay, so these were the examples some examples of application of the Grand Canonical Ensemble. Well, let's try to answer another question that I had mentioned probably on Monday. Okay, when we were looking at the canonical ensemble, we had seen that, okay, the energy doesn't fluctuate. The fluctuations in the energy, although the system can exchange energy with the environment, the fluctuations in the energy will be negligible compared to the energy this system has. So for more practical purposes, our system, if it is in equilibrium, well, it just behaves like an isolated system. The energy is fixed. Let's see if we have a similar case also in this Grand Canonical Ensemble. Can we use the Grand Canonical Ensemble? The results of the Grand Canonical Ensemble, will it be the same as the Canonical Ensemble or the Microcanonical Ensemble? Let's start with the fluctuations in N. The number of particles in my system. Well, just a reminder, the Grand Canonical partition function is given as e to power minus beta e minus mu n, which you can also write as sum over e to power minus beta e z to the n, whichever one you prefer. The number of particles, the average number of particles, let me put the average signs over here explicitly, it will be, for example, if I take the derivative with respect to beta of, sorry, I keep doing the same mistake, derivative with respect to mu of this expression, it will bring down a beta n in front of the exponent. I just want an n, not the beta, so let me multiply by kt of logarithm of q. I'm taking this derivative with respect to beta, with respect to mu, sorry, keeping t constant or beta constant and also the volume constant. This is the average number of particles. Or I can do the same thing as well. It will be essentially the same thing. It will be z times the derivative with respect to z of logarithm of q, keeping beta, keeping t and v constant. Now, they are the same derivatives. Remember, z is e to power beta mu. Since I am keeping t constant in the second derivative, the derivative with respect to z basically means I'm changing mu only. I mean, derivative is just look at how things change when you change one thing, just measure how much the other thing changes. Here in this derivative, I'm changing z, keeping t constant. But if t is constant, beta is constant. So in this expression, in order to change z, I should be changing mu. So that's why both things are the same. And in fact, to see that, I can write this as derivative with respect to the logarithm of z, of logarithm of q. Logarithm of z is just beta mu. Since t is constant, beta is constant. So I recover this expression over here. Now this is the average of n. What I would like to calculate is delta n squared average, which will be the average of n squared minus the average of n squared. This is what I'm interested in, the fluctuations in the number of particles in my system. Well, how can I calculate? Let me look at n squared. I can calculate the average of n squared, 1 over q, sum over all the microstates, all the number of particles of n squared, e to power minus beta e minus mu n. Well, if I take the derivative of that exponent with respect to mu twice, of course, when I'm taking the derivative with respect to mu, I'm keeping t constant and v constant. Every derivative with respect to mu will bring a factor of beta n. So this derivative will just give me a beta squared n squared. I don't want the beta squared, I only want the n squared, so I have to multiply this by kt squared. This is what I want. Of what q? Well, let me write it slightly differently. This is k2 squared, 1 over q. Derivative with respect to mu of derivative with respect to mu of q. I'm taking the derivative twice. Well, you see, when I'm calculating n, it is the derivative of q over q. I would like to somehow relate this expression to n rather than the q, because once I relate everything to n, get rid of the q, the rest is thermodynamics. Thermodynamics allowed me to go from one thermodynamic derivative, express it in terms of other thermodynamic variables, so that's what I'm aiming at. I would like to express all of these rather than not in terms of the partition function, but in terms of thermodynamic properties. That's what I'm looking for, if possible. But to do that, I have to divide this by q. Well, I cannot just divide by q, I need to also multiply by q. So it's just 1.
Isn't that ln
Hmm?
Isn't that ln q?
This one? Not really, because it's the second derivative. If it were the first derivative, yeah, that's the derivative of the logarithm of q. But since here this is the second derivative, I cannot write it as the derivative of the logarithm. But that is what I'm trying to do. Somehow do some tricks so that I can write it in terms of the derivative of the logarithms. Now here I already have a derivative of the logarithm of q. That is nothing but n over kt. Yes, n was, if you look at this expression, n is just the derivative of the logarithm of q multiplied by kt. So if I divide by kt, it's just the derivative of the logarithm of q with respect to the chemical potential. Okay, that is nice. So I have, and keep in mind that in all these derivatives, although I'm not writing them explicitly, t and v are constant. So kt in those derivatives are just constants, so I can get rid of one of these kt's. So that leaves me kt times 1 over q, derivative with respect to mu of q times n. Well, here I'm no longer writing the average signs, but keep in mind that whenever I'm talking about n, I'm talking about the average n. Well, this is, now I can take that derivative. It will be kt 1 over q, derivative of q with respect to mu times n, plus derivative of n with respect to mu. Well, it's again nice because this derivative over here is just n over kt. So what I was evaluating, I'm looking at n squared average n squared average is now, well, the first term, this one, well, the kT's cancel. What I'm left with is just n squared, the n average squared, plus kT times derivative of n by mu at a given temperature and volume. Now delta n squared average, remember this is nothing but n squared average minus n average squared. This is just kT derivative of n with respect to mu at constant temperature and volume. Now, I have a simple expression for the fluctuations in the number of particles. Well, there's still the chemical potential, which I don't like. I would rather express this in terms of other more easily measurable quantities. But I can do that. I had already calculated the differential of the chemical potential. Yes, I already have this expression over here. Well, this is d mu. Now, at T constant, d mu is just V dP. That's nice, because now n squared, delta n squared average is kT over, this is the volume per particle, derivative of the number of particles with respect to pressure at constant temperature and volume. Well, remember what V was. V was V over N, or N is equal to capital V over small v. This is equal to kT over small v, derivative with respect to pressure of capital V over small v at constant temperature and volume. Now, rather than the number of particles, I will be using the volume per particle, which will be equal to V kT over small v. Well, this V is constant, so I'm just taking it out. What I'm left with is, if I take that derivative of 1 over the V, is derivative of V with respect to pressure multiplied by minus 1 over V squared. Which is equal to, well, this is n kT over small v minus 1 over v times derivative of the volume per particle divided with respect to the pressure at constant temperature. Well, you see, let's go back. Now here. Well, this basically tells me that the V is actually a function of temperature and pressure. I can write V as a function of temperature and pressure only. So that is why here I no longer have constant capital V, because volume per particle depends on the temperature and pressure, not on the overall volume. So that's why here I have only the T. But that derivative is actually nothing but the compressibility of the system at constant temperature. Now, this is delta n squared average. Okay, so if I divide this by n squared, the relative fluctuation in the number, you see the fluctuation in the number increases with n. Everything else is an intensive parameter. If I look at the relative fluctuations goes as 1 over n kT over V times the compressibility at constant temperature. It seems as if we take the limit n goes to infinity, this goes to 0. And hence the fluctuations are negligible.
In this equation, why don't I not write the body density as V over n, so that n cancel?
Sure. Yeah, thermodynamic, when we talk about thermodynamic limit, we send n, any extensive quantity to infinity. So V is something of the order of n. Again, it seems as if, I underline this, it seems as if the relative fluctuations goes to 0 in the thermodynamic limit for macroscopic systems. And the reason why I say that it seems as if it goes to 0, well, it goes to 0 unless that compressibility is finite. Remember, what is the compressibility? You look at a change in the volume, change in the pressure of the system at a given temperature. You take their ratio. Well, let's go back. What happens during a phase transition? If you are, let's say, in this region, during the phase transition, V changes, the change in V is finite, but the pressure doesn't change. So this, you see, during a phase transition, delta V can be finite, whereas delta P is 0. So derivative of delta V by pressure diverges. So what this tells me is that, okay, in the grand canonical ensemble, the fluctuations in the number of particles is negligible in the thermodynamic limit unless you are looking at phase transitions. During phase transitions, the fluctuations in the number will be significant. In fact, you can show that this kappa T will behave like n to the delta, n to some power. Now, if you remember what we use this argument of negligible fluctuations in the canonical ensemble. The canonical ensemble and the microcanonical ensemble, well, they will basically give the same answer. I mean, even if you have, I don't know, a given system, let's say this T-chain, it is interacting with the environment. It is exchanging energy with the environment. If I know its average energy, if I determine it somehow, I can just treat it as if it is isolated using that average energy as the energy of my T-change. And the results would have been identical. In fact, we had seen it in a few cases. In the grand canonical ensemble, it will be the same unless we are near a phase transition. In a phase transition, they will give a different answer. The number will fluctuate significantly, and hence you cannot say that the number is constant. Because during a phase transition, it's so easy for the particles to go from one phase to the other one. The fluctuations will be significant. Okay, we still have the fluctuation in the energy. Now, let's look at the fluctuations in the energy. Well, again, let me just, a reminder, the partition function the average energy will be just derivative minus the derivative with respect to beta of logarithm of Q at constant Z and V. E squared average will be 1 over Q E squared Z to the N e to the power minus beta E 1 over Q times the second derivative with respect to beta at constant Z and V. Well, the derivation will be basically identical to this one that we did over here. So let me skip some steps. Now let me write them. This is just the energy. And if you just take the derivative, you will get U squared minus del U by del beta at constant Z and V. Yeah. And hence delta E squared average, which is E squared average minus E average squared. This is just minus the derivative of the energy with respect to beta at constant Z and volume. Which I can also write as delta E squared will be kT squared derivative of U with respect to T at constant Z and V. Okay, first of all, I don't like the Z as a free, as some argument over there. I would rather express everything in terms of N, T, V, P, etc. So let's see what I can do with that derivative. U, I would rather write U as a function of N, T and V. N I can express in terms of Z, T, and V. And the ground canonical ensemble, N is not fixed. The average number N is expressed in terms of the chemical potential. So basically, we solve for the fugacity or the Z or the chemical potential in terms of N, and hence we can express everything in terms of N, T, and V. Now, if I take the derivative of this expression with respect to T, at constant Z and V. Well, I'm basically taking its derivative with respect to N, the first argument, keeping the second and the third arguments constant, then keeping the second derivative of the second argument with respect to Z. That is where one of the temperature dependencies of U. The other temperature dependence is the explicit temperature dependence, plus del U by del T at constant N and V. You see, most of thermodynamics for us is just manipulating the derivatives. First, identifying which free variables you will be using, and then try to express all the derivatives in terms of derivatives with respect to those arguments. And my purpose is to be able to write almost everything in terms of derivative, in terms of N, T, and V. Those are the things that I'm more easy to play with, more familiar, easy to measure. Well, what does this tell me? The fluctuations in the energy squared will be kT squared del U by del T NV plus kT squared del U by del N at T and V, and then del N by del Z at T and V. Well, the first term you can even write it as minus del U by del beta at constant N and V. Well, the first term, you see, what we are calculating at. We are calculating delta E squared average, which turned out to be just the derivative of U with respect to beta. Why do we have Z at constant Z over there? Well, because we are looking at the grand canonical ensemble, and Z is a parameter that appears in the partition function, etc. But if I would do the same derivation, in fact, we did the same derivation in the canonical ensemble. In the canonical ensemble, I will get exactly the same expression, but instead of Z, I will have N constant. So I will take the derivative of U with respect to beta at constant number of particles and V. Number of particles is constant because in the canonical ensemble it's constant. I would get, in fact, exactly this one. So that is nothing but the fluctuation in the energy in the canonical ensemble. So there's the fluctuation in the energy in the grand canonical ensemble is equal to the fluctuation in the energy in the canonical ensemble plus some correction. Now let's look at that correction. There I have some derivative of the number of particles with respect to some parameter Z. Well, I had already studied the fluctuation in delta N squared, which is, well, we had calculated it. It is, let me pick this one. Okay, so let me see. That is what I'm looking for, delta N over delta mu derivative. Now, what do I know? I know N. We had already Okay, let me skip all that derivation. The details are in the book. I don't know if it will be illuminating for you. And I fail to remember the steps because it's hard to see where we are heading to without actually knowing the steps. So let me save all that trouble and just write the final result. So basically, we have this derivative over delta in delta n squared. We first convert it to some using Maxwell-like relationships. N is the derivative of the logarithm of q. Then we convert it to a derivative of u, which we converted to derivative of u. We express it in terms of that derivative over there. And the final result turns out to be delta E squared in the grand canonical ensemble is delta E squared in the canonical ensemble plus del U by del N at constant temperature and volume squared times delta N squared. Okay, this will be the final answer when you play around with the derivatives. Okay, what does this tell me? Delta E in the canonical ensemble was negligible. The relative fluctuation in the canonical ensemble just went as 1 over square root of n. So the first term is, when we look at this ratio, the fractional fluctuation, this term goes as 1 over n. That is what we had seen also when we were discussing the canonical ensemble. Well, for n of the order of 10 to the power 23, that term is negligible. But look at this term. This parenthesis, well, it's an intensive quantity. U is extensive, n is extensive. The derivative of u with respect to n will be an intensive quantity. No. You see, du is minus TdS plus minus, sorry, TdS minus PdV plus mu dn, which tells me that mu is del U by del N, almost that derivative over here, but in this derivative I have the entropy and V constant, not the temperature. That's why it's not the chemical potential. But it is intensive. It doesn't change with the size of my system. And there is no reason for it to diverge. It will be some finite number or go to zero. It will be some finite number. But then the fluctuation in the energy, the relative fluctuation in the energy, will be related to the fluctuations in the number of particles. And again, as we had seen before, the fluctuation in the number of particles will be negligible if we are not close to a phase transition. But close to a phase transition, at the phase transition, that fluctuation will not be negligible. So basically, the lesson of this second hour is that grand canonical ensemble, or the microcanonical ensemble, they will give you the same answers for every system that is far away from phase transitions. But at the phase transitions, they will give different numbers. So we cannot just use a canonical ensemble to study a system on the phase transition, because canonical ensemble assumes that the number of particles does not change. But this tells me that at the phase transition for our system, the number of particles do fluctuate significantly. Okay, any last questions? By the way, I do strongly advise you to go over these derivations on your own. Book closed, notes closed. And just following them, you will not really learn much. You will not learn the reasoning.